Welcome everybody to the first part of the XMOS workshop today. First part is introduction to embedded multi-core theory, hardware and programming, explaining the XMOS architecture, the chips, the applications and the development tools and our development kits, hardware kits. This afternoon we will use one of the kits to do some development of a servo motor control and cap sense. My name is Thomas Gmeinde. I'm an FAE for XMOS. Been with XMOS for 6 years now. And yeah, there's my colleague Rob Fischer here, who will do parts of the presentation and also help me with the workshop later. So this is the agenda, introduction to xCore, talking about XSOFTip, which is a library of interfaces and IP components, software IP, and then what applications they enable. And then we're going to introduce our development tools and talk about the XC language, which is based on C, but it has some extensions for multi-core programming and deterministic I/O programming. And then we will talk about our development kits that you can use to realize various applications. So I will have around 60 slides. I will go through some of them very quickly. If you have some burning questions, feel free to ask them, so that we make a good use of 1 hour. Let's talk about why multi-core is important for embedded systems. You can partition the system functionality into discrete tasks, and it's important that they run independently. For the real-time performance, you want independent execution. They shouldn't interfere with each other. And it's also important to have very timing predictable code, especially if you want to do hardware interfaces in software, which is what we also do. And usually you only know that from an FPGA, but this is a processor, so that's what's really special about it. But this will make more sense when we look at the architecture block diagram on the next slide. Because of this deterministic architecture and the fact that we can react immediately to events, we can react 100 times faster than conventional processors. How is this possible, you might ask? So it's illustrated here how the architecture makes that possible. What you're looking at here is an xCore tile. That is a building block of our architecture. It has up to 8 logical cores. You can use multiple of these tiles to scale up the multi-core architecture and performance. Each of these cores is linked directly to the I/O. So there's no memory mapped I/O that you know from conventional micros. When an event happens on the hardware, we react immediately to it. And I will illustrate how this brings an advantage in terms of responsiveness and determinism. We call this event-driven. The logical cores communicate with each other using this X-Connect fabric. This is a zero latency communication on the tile and very low latency to other tiles. So again, very deterministic. Keep in mind that with this architecture we can do hardware and software. So one of these cores can implement an Ethernet MII interface or a CAN interface. And to implement hardware, you have to react exactly when the event happens, when you get the valid signal from the PHY. You cannot wait for other interrupt handlers to finish. And using this, we can guarantee fast response times, and we can also ensure 100% timing determinism, and we use that in our tools, and Rob will tell you about this later. So it enables static timing analysis of embedded software. And let's zoom in on one of those logical cores now. A core is either running or waiting for an event to happen, and events can happen when something on the I/O occurs. So for example, the valid signal on the Ethernet PHY goes high. That's when I react and load in the 4 bits or the nibble from the Ethernet PHY, the data. You can get an event from other cores. So to continue the Ethernet example, the MII interface would receive data from the Ethernet PHY and would send that data onto another core, which is a higher level protocol like an AVB MAC, for example. And above that would have a 7022 listener. This example is from an Ethernet AVB stack. So cores pass data onto each other, and that also causes events. And of course, we need to be able to create timer events. And it's important to note that the whole time a core is waiting for an event, it is paused and does not steal any CPU cycles. So it's a very efficient processing scheme. So up here you see a traditional interrupt-based system with an RTOS. So an RTOS running on a micro. When an interrupt happens, there will always be some OS overhead to do, and then some overhead to do the context switching. Then you service the interrupt, and you have to restore the context, the previous context, and then already the next interrupt is queued up. So that clearly shows that interrupts interfere with each other. In contrast to that, on the XMOS architecture, we react immediately to an event because the cores do not interfere with each other. And you see that the response time to an event is very small, very low, and always constant. And that means we are deterministic enough to do hardware and software. You see up here in the interrupt-driven system, your latency varies depending on how many interrupts occur. And that brings non-determinism to the application, which is bad for real-time performance, right? So here you see in one glance the advantage of the event-driven execution scheme of XMOS. What does that bring to you in your application? So again, we react very fast in around 100 nanoseconds to an event, and the reaction time stays constant. So that means you can scale the number of events that you're processing. You can scale the I/O events or the PWM control, for example. So this afternoon we will develop a servo motor controller, and one of our customers has actually created a spider. It's a very real looking thing. It has 26 servo motors in it. So you can, when you can control one thing, you can very quickly scale to control several things with the same accuracy because your response time stays constant. And again, on a traditional interrupt-based system, the response time rises with the number of events to be processed. And you can also see this is non-linear here. So while XMOS can react in 100 nanoseconds, this measure or this study has shown that the other micros take a lot longer. So there's a white paper if you want to have more information about this. You can download from the University of Denver. Just an overview of the I/O. So the I/O ports are intelligent in the sense that they offload processing from the pipeline. So you can program a port for timed input. You can say sometime in the future input a value, and then that whole time the processor will pause and the port takes over the processing. Timestamping is important for something like UART or PWM. You want to know when an event happens and then do something in the future, a defined number of cycles from that current time. Predicated input is also important. I mentioned the example of an Ethernet PHY, where you only want to react to, you only want to input the data from the PHY when the valid signal is high. So you can tell the port only wait for that event. So that's clock port with a strobe. Predicated input is waiting for a certain value on a port. Again, it's a good example of offloading processing because it could take a long time until some value occurs on the port, like from a rotary encoder, and that whole time the core is waiting and not wasting any CPU cycles. And finally, serialization, deserialization, very helpful for serial interfaces such as I2S. So here's an overview of product families. We have a general purpose family with 4 to 16 logical cores, a USB family which adds a USB PHY, 8 to 16 logical cores, and an analog family. This adds ADCs integrated and power supplies. By the way, these power supplies and ADCs are also part of the USB family. And then we have an extended architecture, which means you get 7 logical xCores plus one Cortex M3. And here's an illustration of it. So 7 logical xCores and an ARM Cortex M3 with low power peripherals. Here's an overview. Really, it just summarizes what I just said, so I'm going to carry on because I have like 1 minute per slide. So, now I want to talk about what applications this architecture enables. As you can probably tell by now, it's very flexible. We program the I/O in software. What does that enable? So, we have software IP for all these interfaces, USB 2, Ethernet with AVB. So AVB is real-time Ethernet for quality of service, audio and video streaming. Several audio interfaces, I2S, SPDIF, also TDM, then DSPs, DSP functions, bytecodes, FIR, PWMs, PIT, and then the standard serial interfaces, and also for automotive CAN bus. And Ethernet AVB is something that is becoming very popular in automotive. Because Ethernet is providing a lot of bandwidth. So all these are available as what we call xSOFTip to build your system. And this is how you would build it. So this just shows that a xSOFTip component usually uses a logic core or a part of a logical core, some ports and some memory. So this could be your MII interface, for example, for a Ethernet application. All this IP is available in the development tools. So if you're joining this afternoon, you can see that in the tools you have all these interfaces. So where you see a little Lego icon, that means it's a reusable component, such as CAN, Ethernet, UART, USB, etc. And where you see a play icon, it means it's a demonstration you can run. So you can very quickly evaluate the technology. So you can very quickly build a USB device, for example, and realize a USB printer. There's also application notes for these types of things on the XMOS website. And here's an overview. Really, it's 4 major application categories. So very flexible architecture. You can do lots of stuff with. It solves lots of real-time problems. Let's start over here. Multi-channel audio connectivity. USB audio can be used in many applications. It's very popular in high-end audio, high sampling rates, low latency. Low latency is also very important for prosumer space, like DJ controllers. So this is an integrated digital DJ controller where you want very low latency in terms of the time between moving the jog wheel for scratching and hearing the effect of the scratching. So you need a low latency real-time machine, which is what XMOS is. There's other interfaces like SPDIF, MIDI, and bridging to Ethernet. And a third market for USB audio is Pro Audio, so where you have a high number of channels going over high-speed USB. Robotics, so this is that spider I told you about earlier. It has 26 servo motors controlled by one XMOS chip. One of these xCore tiles runs at 500 MIPS, I should have said. So you get a lot of performance. And one of these tiles is enough to control 26 motors and run an inverse kinematics engine. So you can check it out on YouTube. You can actually dance salsa. Automotive networking. Ethernet AVB, LIN and CAN. So in the car there is a physical layer called OABR, Open Alliance Broad Reach. It's 100 megabit full duplex Ethernet over a single twisted pair. So this saves a lot of cost. That's why Ethernet in the car is becoming very popular now. We have an AVB solution for this. General connectivity. So this is really looking at all the interfaces that we support. You saw some of them on the slide early, on the introduction slide for xSOFTip, USB, Ethernet, CAN, bridging between those interfaces. Bridging things to things. USB to things for printers, for USB to UART bridges. So you have, a very flexible USB device. Then you have all these standard serial buses, and you have field buses, and you have also Ethernet. So get creative. Bridge between any of those. And again, we can easily scale to multiple interfaces. So so we approached by a customer that wants to have 5 CAN interfaces and 1 Ethernet interface. There's no standard microcontroller that does that. But with XMOS you can do it in software. So that's one of these examples where it's very attractive and economical to use that chip, because we are cheaper than an FPGA and a lot more flexible than a microcontroller. Here's another example, USB to quad UART, Ethernet DC. DC stands for daisy chain, so you can chain these endpoints together because they have 2 Ethernet ports. And on the other side you have several CAN interfaces. Here's Ethernet to 8 UARTs. And here's an animated slide to show audio connectivity. So you have USB. USB audio uses isochronous endpoints to stream audio in both directions. You can add AVB, audio video bridging over Ethernet. And you can use several standard audio interfaces to codecs, I2S, TDM. TDM usually is also what DSPs are using, so if you need some more heavy DSP lifting, you can connect it via TDM, SPDIF, and ADAT. So I should have said something about the color code. The orange blocks are xSOFTip blocks that you can get directly in the tool. And the purple is custom code to bind it together, to bridge between those interfaces. Again, your standard serial buses. And then, you can, so the APIs internally to all these blocks are documented in the tools as well. So essentially what you're doing here is you're calling the API functions, you're receiving data from USB and you're sending it out over Ethernet, for example. Same goes for CAN and the others. And you can add DSP functions in that data path. So let's say you're streaming from USB to I2S, then it's very easy to spend an additional core to implement DSP functions. Because the cores communicate over the channels, so you just put another core in, stream data into it, do the DSP and stream it on to the next core. So it gives you a very low latency deterministic data path. Some more examples, automotive networking gateway, 2 ABB interfaces and CAN. Also very interesting, we can support video and audio over ABB. So you can connect several TV tuners. So cars in the future will have several tuners, so people don't have to agree what to watch anymore. You can watch independent channels, so the kids won't fight in the back over which channel to watch. So 2 DVB-T receivers and 2 digital radio tuners over AVB. Audio-video bridging. Telematics unit, AVB to USB and CAN, and robotics. So here we have a new color. The blue blocks are blocks that are delivered by a partner. So we have a partnership with Synapticon. They are a company doing robotic solutions and motion control solutions. Cyber physical systems, they call it. So it's for next generation robotics where you need the robots to be intelligent and know where the people are and not hit them in the face. and know where they are in the environment. So we partnered with them to create a motion control solution, which you see here in blue. So this is for 4-axis mobile platform, like a quadcopter, right? So quadcopters have BLDC motors. Synapticon has an excellent BLDC solution, and it would look something like this. You will probably have also an accelerometer connected. That concludes the xSOFTip and what application it enables. I hope we'll have some time at the end for questions, but if you have any burning questions, then you can ask them directly. And Rob will now tell you about the XMOS development tools, which are a very important ingredient to put all this together.
So before we start, I'll just introduce myself. My name's Rob Fisher. I'm an FAE for XMOS. I've been with XMOS for nearly 9 months now. So just about getting to grips with it. So any tricky questions, direct them at Thomas, and I'll take the easy questions today. So, as Thomas said, the tools, very important aspect of what we offer. And this slide is just illustrating the two variants of the tools that we have, the Enterprise Edition on the left and the Community Edition on the right. I'll just describe the Community Edition first. This is totally free. You can download it off the website. You have to give us your email address and name, and that's all we ask. And you can download these tools, and the Community Edition has the latest upgrades, the latest features, and it will link to our support channel, which is xcore.com. I'm not sure whether anybody has seen this, but this is a forum, a very active forum of community users that post details about projects and pose questions, etc. On the left here we have Enterprise Edition. Now this is, there's a cost associated with the Enterprise Edition. This is it may not contain the cutting edge updates that we've done, but this is tested to be stable. So we know that all of the xSOFTip, which Thomas talked about earlier, will work with this edition, and it hasn't got the latest updates, so it's less likely to bring out bugs in the latest cutting edge updates that we release. It's license-based bug fixes against historical enterprise releases. So if you are producing a product based on our device, you may choose to go to the enterprise tools because you're guaranteed support, and we will support IP for previous versions of the enterprise tool. And this is an important aspect, support through xmos.com. There is a ticketing system that you get with the enterprise tools that connects you directly to an engineer. So this is the development environment. It's based on Eclipse. We'll go into some more details in a little bit, but this is just showing that you have all of the tools required for a system on chip. You have xCore development code there. This is the ARM, so this is illustrating development on the XA platform that Thomas mentioned. Got all your build files, your make files on how to build your project for both the xCore and the ARM. And here you have in this corner, and we'll describe this in a bit more detail in a second, this is the xSOFTip that you will use to create your application. And when you've built your application, you're going to run it, you want to debug, and the IDE switches into another mode, the debug mode, and you can, it's very advanced debug features. So we have the debugger information here, breakpoints and code, and these two parallel windows is the xCore and the ARM. So if you are debugging in parallel like this, you can trace through the interactions between the xCore side of your application and the ARM. So we use an LLVM compiler, which some of you may be familiar with. This is relatively recent switch, and we found the optimization in the compiler to be excellent and has given us a performance advantage over our previous version of the compiler. So now going into a bit more detail about the tools. We call it XTime Composer. Now this is the suite of tools we give you to develop your application. As I said, it's based on Eclipse. There is a command line tool which some developers prefer, and it has all the functionality of the Eclipse environment. We've spoken about the compilers. So we have xSOFTip Explorer. Now this is the way we present the xSOFTip to you. It allows you to see what IP is available and also see what resources it consumes, like the number of cores, for instance, the amount of memory it takes. These are important factors when you're pulling together your design. XTA, I think Thomas mentioned about the timing analyzer. This is something that you don't usually have in a microcontroller environment. You're more familiar with it when you're working with FPGAs, having a timing analyzer. But it's a very powerful tool. Xscope, this is an advanced debug tool. And there's some pictures in a minute. But this allows you to actually get inside the chip in the same way you might think of using a chip scope in an FPGA design, a Xilinx FPGA design, to get right inside the design and see what signals are doing in there. Xscope allows you to get right in there. XSIM as well, this is a simulator for your design. Again, more familiar with in an FPGA world that. And the debugger. And all of this functionality is free of charge in the community edition. So this is the development environment here. We have all of your source code here on the left. This is the xSOFTip, so these are the blocks you can use in your design. Your code window, console in Xscope so you can get trace. And this is the developer column. So this links into the documentation on the website. So for instance, if you click on the SD-RAM interface, you want to know how to use it. In this window, the documentation will appear and links to examples and other projects so that you have all the information you need in the development environment as you need it. So this is our debug adapter, which uses one of our devices, in fact. It connects via USB to JTAG, so our device in this instance basically implements a USB to JTAG connection. But in addition to that, there's because it's one of our own devices, we route what we call the XConnect links, which I don't know whether you remember on the diagram, there's a block over here which XConnect, and that allows you to connect multiple devices together. We connect these through, and this creates a high-speed link from the device under test back to your host debug environment via the USB connection. So this allows you to do real-time interrogation of signals and values within the chip with very little impact, and I think this is the next slide, very little impact on your code that you're debugging or using, which in a real-time embedded system is imperative. If you're trying to debug a real-time project and you stick a breakpoint in, your real-time project is no longer real-time because everything's halted while it goes and transports that data back to the host for you. But using the Xscope and our debug environment, the code it won't halt, and you can maintain the real-time interactions that are important. So here, this is an illustration showing, I'm not entirely sure what the application here is, but in the code, we've assigned an Xscope signal to look at a value, and here we've got an analog representation of the signal over time. And this can update at about 1 megasample per second, which is pretty impressive. So Xscope, this is, it allows us to get inside the device. Very useful. I when I'm working with the with XMOS projects, I don't bother trying to do JTAG debugging anymore. It's all using the xScope functionality. It's a very simple interface within the debug environment. You don't actually need to know the complexities of the interface. It's just a link. You select that you're going to use the xScope functionality, and it's there. And this final point is a really interesting point. Because we have this link to the chip back to the host PC into the development environment, you can actually connect into that data pipe, if you will, with your own external applications. So for instance, LabVIEW or GNU Plot, and get your data plotted outside of the development environment. In this example, it's saying that you could also hook that into Wireshark, for instance, as a network analyzer. So this is the timing analyzer that we spoke about. This diagram here is saying it's analyze your code, and this is showing you in a diagram the best case and the worst case routes through your code. So if statements and jumping in and out of functions, etc. So you can use this to analyze your code and decide where you need to focus on optimization or restructuring your code to meet your real-time requirements. So previously we'd arranged that Thomas was going to jump in here, but I'm enjoying myself now, so I thought I'd carry on. Give Thomas a break. So this next section is about how you program the device. 90% of the coding you will do on an XMOS device is C, or C++, in fact. But there are some constructs that we need to define that allow us to make use of the architecture. Parallelization, for instance. But here we're just showing that the XC language is principally ANSI C. There's a huge overlap, and there's just a couple of constructs that we've defined to allow us to make best use of the architecture. So XC2, there was a previous version of XC. XC2 is the version that we're working with now. And it also includes some abstractions to make communication between cores much easier and transparent to the user. So hopefully when at the end of this section, you'll know a bit more about what the constructs are that we use to describe the functionality and how to handle asynchronous events, independent asynchronous events. And I don't think, then there's also, as Thomas was describing, the hardware response port, so offloading some of the functionality from the core into the hardware response. That also requires special constructs to define that, so we'll come on to that now. So XC, XTendC, these are the some of the additional things that we've defined. Additional data types, port, that's pretty obvious. A timer, so this is a hardware blocker timer, and you can reference it from the code. Chan and ChannelN, this is the communication structure between cores, which is important. You've got functions that are working individually on cores, unaffected by each other, but you need to communicate between them. These two symbols are the way we communicate to ports and channels. So input and output, pretty self-explanatory. Select is when you're working, I think it should be the other way around actually. So let's talk about par first. Par is the way that you structure your code to operate on different tiles, and I think there's an example. But par, all of the functions that you've defined inside the par statement will run concurrently on separate tiles. And the select statement is the way that you define how the core responds to events that occur. And that event could be a port waking up and saying, I've received data, or a timer expiring, or another core saying, here's some data, go and process it. So this is the par statement. It's pretty simple. I mean, even even these additional constructs that we've added look very C-like. It's not too alien. This instance is saying within this pass statement there are two functions defined. These two functions will be placed on individual controllers and operate concurrently at the same time. So they will have no interaction. If this one stalls and waits for something, it does not affect the functionality of G. So in a multi-tile device, if you can remember, Thomas said there was 8 cores on a tile. We have devices that have 16 cores, which have 2 tiles. When you have a 16-core or 2-tile device, you need to say which tile you want a particular function to run on. And this is this on-tile construct there. Communication between cores. This is achieved using channels, or interfaces is the latest abstraction. And this allows you to define a path between 2 functions, and then the compiler will make the best choices about how to implement that communication structure. Channels, so this is an example of how to use channels. You define a channel, and this is a link, remember, between 2 cores, channel C, and here we're saying take a data sample from the channel and put it into variable X, and the inverse is true here. Put whatever's in variable Y into the channel, and then it will be received on the other end of the channel in the same fashion. So ports, this is how you talk to the external I/O of the device. Again, similar construct to the way you talk to channels. It's a value that's on port P, place it into variable X, and the converse is true there. So this is a diagram of what's actually in an I/O. A surdas, which is an important aspect, and it's really one of the ways that we offload processing from the core into the I/O. So, for instance, if you had a serial, a 1-bit input, but you wanted to treat it as a 32-bit input, you wanted to read these as 32-bit words, the surdas will parallelize this single-bit value over 32 samples and just provide the core with a 32-bit word. So the core isn't taking a bit, shifting it, taking a bit, shifting it, taking a bit. The core's just waiting. It's doing something else until that data sample is given to it as a 32-bit word. And all of these blocks, in fact, are the way that, I think this is on the next, yep. The way that we achieve the offloading from the core into the hardware response ports. So you'll recognize this slide from Thomas's discussion earlier. These are how you achieve this functionality in the code. So X goes to P, so whatever's in X, put it out to the port at a particular time. And the inverse is true here, so P goes to X, and then the time it occurred is stored in variable T. Conditional input, so P, when pin is equal to 0, assign it to X. So for instance, in an Ethernet interface, you may want to look out for starter frame character or preamble 55, and you could do this. You say, when this situation occurs, generate an event and start processing. Synchronization, so you can assign clocks, and this is another hardware block, and you can assign IOs to be synchronous to that particular clock, which synchronous interfaces is very common. So this is a very important aspect. And this final one is the serialization that I mentioned earlier. So here you define the port. Here it's a 1-bit port, but we're going to treat it as an 8-bit port. So we're going to throw 8-bit data at it, and it will be serialized on output, and the inverse is true on input, and the other way, deserialization as well, from 1-bit to 8 or 32. This is a bit of a slightly more in-depth look at the architecture, and it may not make immediate sense, but I'll describe it anyway. On the right-hand side here, we have the ports, and these are all 1-bit ports. But in terms of the code that you write and the interface that you have into them, you can treat them as a 32-bit port, 16, 8, 4, or 1-bit. And this diagram is set out to show you that if you interface to these ports in 32-bit mode, it's actually going to use these ports here. So you can't then also interface using these 4-bit ports. So this is the number of ports you have, and how you interact with them depends on what's suitable for your code. This is a spreadsheet that we give you. You can download it on the website just to help you map out what ports are available, how you connect things up on your hardware, and then how you will interact with them in the software. So timers, this is the event-driven processing. Timers is a hardware block inside the device, and a timer can generate an event which can wake up a device. And here we go, the next slide is talk about this. So defining a timer, then we say at this time put time t into x, and then you know what time it is, so you can define a time in the future to do something. So t when time after t plus period, do something. And this goes to your question earlier about having multiple events dealt with in the same controller. We use the select statement. So this is like a case statement. So within the select, you define events that you want to track within this core. So for instance, here, p input is a port, and when something arrives on the port, put it in variable x, and then you can have some code to deal with that variable x in whatever manner you need. But also you may want to have reports, say, so x, you could accumulate x or average x, and then once a second you might want to output an average. So you have a timer, and then say once a second, output the average value of x to a channel or whatever. And you can keep on adding things to this select statement. All of the things inside the select statement will run on a single controller. So you need a single core, yes, absolutely. So this will be inside a function, and that function will be declared in a pass statement. So you may have multiple functions in the pass statement which will run concurrently, but within the function, this is a sequential operation. So putting it all together, this is an example of it's the example that we were just looking at, in fact, where you have a select, the port is dealt with there, and then we have a timer to do some functionality over the top of it. This is a bit of a fuller example. So ChannelN, this is communication in between cores, and you can see you can use it, construct the select statement in the same way you would with ports. When you get a value on the channel end, do this. When you get a channel on another channel end, do this other task. So there was probably not enough time spent on the XC language to really do it justice. It's a very powerful language, and it really makes best use of the unique architecture. But it's probably one of these things that getting down, looking at the code, seeing how it works is the best way to understand. And I don't think the XC language is at all complex. And once you've understood the architecture of the device, the XC language just makes sense because you know that you need to be able to describe these additional functionality, and XC is the way you do it. So I'll briefly talk about the development kits that we have, and then we can have some time for questions. Maybe you'd like to just pass that around. We have different variants of our development kits. startKIT, which is what's shown in this box here, is our low-cost startKIT, $14.95. And this is a very functional device. In fact, it's an 8-core device. It has ADCs. It has a lot of IOs pinned out, so you can start using this very quickly and get right inside how to work with the xCore environment and the xCore controllers. SliceKIT. So this is our more fully featured development system. I'm not sure whether there's a picture. Yeah, here we go. We have these connectors here, which allow you to construct a system based on the development board and these slices. So this one here is an Ethernet PHY, just plugging in a multi-UART slice there. And this is a range of slices that we have that allow you to construct your system in a development, to evaluate it, to develop with. Ethernet multi-UART, LCD, GPIO ADCs, SDRAM, Wi-Fi. And you can also, all of the code, all of the hardware, resources, schematics, bombs, etc., are available on the website, and you can get the dimensions of the slice and create your own slice with your own peripheral that you need to work with. This is some information on the startKIT, which is just being passed around. 500 MIPS distributed across the 8 cores in the device, 600K of RAM, 8K of OTP memory. We have 256K of external flash. Now the device boots from external flash, so that is necessary, but you can also use it for storing data as well. You can access the flash via SPI, and it can be directly powered from a USB connector. If you bought a startKIT, what would you do? You can go onto the website, startKIT started, and download an example. There are at least 10 examples just on the website that you can download. Look at the code, modify the code, see how it works. And we have the community website, xcore.com. There's a page on there that you can post your project ideas, and there are hundreds of ideas of things that people have done with startKITs, and it's really impressive the range of things people have achieved with the startKITs. So this slide just illustrates some of the resources we give you, and I think this is my last slide, so we'll have questions in a second. This is the link to the tools that you can download that we covered earlier. These links, SliceKIT products, these are the development environment, reference designs, development boards. Examples, all available on the website, so support is where you get the documentation from. xCore community, xcore.com, that's the forum that we've discussed. And also, in addition to that, we have a GitHub repository which has a lot of code, DSP functions, SD card interface that the community has put together. Now, it's not verified by XMOS, but it's code that you can use, evaluate yourself, and work with. And that's everything that we had. So, thank you for listening.
Thanks, guys.